last time. So essentially what we have done till now is we have discussed Newton's laws for the past two classes or so. Discussed Newton's laws, the conservation of momentum, linear momentum, and we have taken some examples, right? Yeah, rocket propulsion, right? And we have taken some examples which basically tell you about the application of these laws or principles. Rocket propulsion is a very illuminating problem. Why? Because this is one of the problems where the mass is changing. So Newton's laws, which is the rate of change of momentum, which we always tend to write as mass times acceleration. So the mass actually here is changing, and so it's the dm, dt's and all, like we saw last time, they enter into the calculation. So this is one example where we kind of use Newton's second law and the conservation of momentum simultaneously in a single frame. Okay, so today will be mostly a discussion class where I'll basically introduce you to concepts of something called conservative forces, okay, first of all, then move on to work energy principle and conservation of energy, mechanical energy. And tomorrow we'll take up problems on these principles. So first of all, conservative forces. So what are conservative forces? Any idea? What are these? Have you heard of this term before?
Yes, sir.
What does it mean, or what do you mean by conservative forces as such?
Work done in a circular path.
Path what? Path dependent or independent? Independent. Okay, good. So the idea is, when we talk of forces, forces basically come in two broad categories. One is conservative forces and the other is non-conservative forces. Conservative forces are those where if you have a given force field, like let's say the gravity force field, the gravitational force field, then the work done in order to move a particle from point A to point B is independent of the path that you take in order to reach from A to B. So in that sense, the path independent thing comes. So what is path independent? It is the work done to move the particle from point A to point B. The point is, suppose you have a point A here and a point B here. So obviously there are infinite, in principle there are infinite number of paths to go from A to B. Go like this. Obviously there's a straight line which is the shortest one, and then you can come up with many such paths in order to go from A to B. Now, amongst these infinite number of paths, obviously the straight line is the shortest one. I'm not talking about displacement. I'm just talking about an initial position A, this is initial, and this is the final. So in order to move from A to B, if the work done is dependent on the path, then it would be a non-conservative. And if it's independent of the path, then it's a conservative force. So this was all in words, but let's make it more quantitative as to what conservative forces are. So one way to define conservative forces is the force can always be written as the negative gradient of a scalar function. This scalar function is nothing but the potential energy. This is the potential energy. And in general, in 3 dimensions, it's a function of x, y, and z. Likewise, the force will also be a function of this is what we face. Oh, this is a permanent one. I shouldn't have done this. I have to switch to the green one. Sorry about that. Not sure what to do with this. Just stay here forever. Huh? If I write again, and erase this. How do you erase this? Oh, write on it again with the same pen. You mean like this? Ah, yes. But then I have to be that precise. Oh, yes. That's very difficult. Okay, I'll ask you to do that. I'm just kidding. Okay, so conservative force fields can always be written as the negative gradient. Remember the gradient sign from the vector class discussions that we had? The gradient effectively in 3 dimensions is, if you just take Cartesian, it's just this I cap del x, all the partial derivatives coming, right? So it's only true for conservative force fields that you can write it as the gradient of the scalar function, this function being the potential energy. Example of that would be the gravitational field. Example would be the gravitational field. How is that? Okay. So in gravitational field, you have the U. You must have gone through this maybe at some point. The U as a function of R. Suppose you have two point masses, M1 and M2. How do you and they're separated by a distance R. So these masses might be the Earth and the Earth and the Sun system, or might be the Earth interacting with another particle, another star or planet. Any two masses, M1 and M2. Then the potential energy is given by G, M1 and M2
by R.
The word R. It's an R, like R. Right? And it usually comes with a negative sign. Okay. Now, if you have to find out the force, what do? You take the negative grad of that. So in this case, it's only dependent upon R. There are no further thetas or phi's involved. So you just have to take the derivative with respect to R. So let's do that. F will be equal to minus dUr dr, and it comes with the direction because F will have a direction, and that's the unit radial vector. If you take the minus del R on this one, you just get G M1 M2 over R square R hat. So this is the standard gravitational law thing, and it only arises because you can write the force as a negative gradient of the potential, and likewise for the electrostatic field as well. Gravitation and electrostatics are very, if not the same phenomenon obviously, but very close to each other in terms of the expressions that you see. Remember the force in electrostatics, Coulomb's law. This is just like the Coulomb's. K Q1 Q2 over R squared. Also the potential energy in Coulomb's law goes as 1 over R. So everything is kind of carried over. Obviously there are differences. Gravitational force is always attractive. In electrostatics would be repulsive, depending on the kind of travel. Also the range. Both are infinite effectively, but the magnitude of gravitational force is much bigger as compared to electrostatics. Okay, those are different stories. But one standard way to define quantitatively, to define conservative forces is that it could be written as a negative gradient of a scalar. Okay, now comes the work aspect through which we can define the same thing. So the work, as we know, is defined as if you move from point I to point F, initial and final. So this is basically the work done. F dotted with ds. What is ds? ds is this infinitesimal displacement. Work is the dot product or the scalar product of the force applied dotted with the displacement. So the work done, what does this integral then signify? It's basically the work done in moving the particle from an initial position I to a final position F. Okay. So now let's do the same thing for the gravitational field again and see that this argument that we kind of qualitatively talked about, that the work done would be independent of the path. How is that true, or how does that hold? So the force, we just figured out the force. This. I'll pull out all the constants outside the integral. Then it's just r cap over r square dotted with the ds I'm writing as dr. Everything is in the radial coordinate. And let's say you're moving the particle from this initial point A, which is my I here, and the final point here is F. So I'll call that R1 and R2. Those are the limits of the integral. Now what is r cap dotted with dr? It's just dr. Why is that? Because that's the cosine of 0. So r cap and dr, they are having the same direction. So the cosine 0 is just 1. And r cap has a magnitude, it's a unit vector. It's a magnitude
1.
So it's just dr. So that's basically Gm1 f2 r1 to r2 dr over r square. Good. If you do the integral, then you will get 1 over r1 minus 1 over r2. Because 1 over r square, if you integrate, you get a minus 1 over r. Minus 1 over r, you do the limits, you pick up 1 over r1 minus 1 over r. Now what does this tell you? This is the work done in moving the particle from this point to this point. See, it just depends upon r1 and r2, which are the initial and the final points, with respect to some origin, wherever the origin is. I mean, this r1 and r2, let's say this is r1 here and r2, and that's my origin. Doesn't really matter where the origin is, but the point is, if you have the origin fixed, it will only depend upon the initial and the final coordinates. It doesn't really care about which path amongst these several paths you take. It will just depend upon the final two, initial and the final two coordinates. So in that sense, that's where the path independent definition of conservative forces comes. Now obviously this won't be true if you have a non-conservative force like friction. It will depend. Take a very simple example. If you have to drag, let's say, a block of mass on the table, which is obviously having friction, then from moving from point A to point B, the number of paths you take, or the different kinds of paths that you take, will, the work done due to friction, will actually be different for each of the paths. Why is that? Because if you take the shortest one would be the smallest work done. If you take a longer path like this, obviously the dissipation due to thermal friction, thermal energy would be higher, and hence the work done along those paths would be higher, or rather dissipated in other sources of energy, other kinds of energy. Okay. So friction is the most standard example of a non-conservative. So there you cannot do this. There you cannot write friction force. F cannot be the friction force. It cannot be written as a negative gradient of a scalar. Neither does this one. Okay, and just to sum this up, so suppose the initial and the final coordinates are the same. That is, if you come back to the same point, then the work done, you can write this as an integral like this. This will be what? What do you think this integral will be? So what this circle here means is that
Circular path. Surface.
right, you are taking a closed loop. Okay, but it's a line integral, not a. Don't confuse it with Gauss's law. There are also these DS's appear, but DS here is a line integral, not a surface integral. And also, it's a force here. In the Gauss's law, it's the electric field, not the force. Okay. So what will this integral be? What's the value of this integral? Closed loop, F being a conservative force. What will this integral give you? So you are starting from the initial position and making a closed loop such that you come back to the initial position. It's a situation like, let's say this. This one. So you are making maybe I draw it. So you start here, and whatever you do, you come back to the same position. So this would be like a closed integral like this. So what do you think the answer would be?
0.
0. Exactly. 0. It would just be 0. So these three. So this one and this one, they are kind of alternative definitions of conservative force. Mathematical definitions. Number one, it can be written as a gradient, negative gradient of a scalar function, like potential energy. And the work done, if you do a closed line integral of the force, it would always give you 0. You can see that from here itself. If you come back to the same location, what do you think R1 and R2 are? They are the same. R1 and R2 are equal. So this will just give you 0. That's represented here. Okay. Any questions here? All good? Okay. So now I need to erase this. What's the best thing to do, you're saying? Draw on top of this. No, that's not work. Bad? It's not the best way to do things. It does work, but it's more work. Luckily, I haven't built up the code with the permanent part. I realized later it's a permanent part. And things being this permanent in real life would have caused much of a problem. Luckily, you can erase things. Let's see. Does water help? Huh? Eraser. Eraser of what kind?
Rubber.
Pencil eraser. That does. That does work. Do you have one? Okay. Let me try it. Yeah, actually it does. Damage your eraser. Maybe forever. Is that fine?